Today during class, we're talking about section 6.7, sufficient statistics. We're almost finished with this section during class with a little bit left over. So let me try to review this and finish up 6.7. And basically, a sufficient statistic is um, it is a function of the random variable x1, x2, xn. We see this function is sufficient for theta if and only if you're able to factor the likelihood function into two parts. One of the factor h function does not depend on theta. One of the function phi, depend on theta, but only through the function u, which is the function that we are calling sufficient statistics. In class, we went through three examples. The first example is the Poisson distribution. If you construct a likelihood function for n random variable of a Poisson distribution, you will multiply their probability. In the multiplication, many of the factors can be combined together. And then we factor this into, and then according to what we have here, x bar will be a sufficient statistic for lambda. If we got a normal distribution with variance equal to 1 to estimate the mean, again, we can multiply the density function. And then in this multiplication, we can combine the term and create an exponential form. Insert x bar, we see that this function can be factored into two components. One component depend on the x value only, one component depend on the x bar and mu. So this again is showing x bar is a sufficient statistic for mu. The third example is a Bernoulli distribution example. We can have n random variable from Bernoulli distribution, and the likelihood function will look like this. And in this situation, the term can be combined because the exponent can be added together. Summation of xi becoming the sufficient statistics for the parameter p. All right, having all of these, we're able to come up with the idea that if we are able to if we're able to rewrite the density function into exponential form in the exponent of the exponential form, the first part is multiplication between the variable x function with the function of theta. The second part is a function of x only. The last part is a function of theta. Then only the first part that has a key of x, the key summation of kx, would be a sufficient statistic for parameter theta. So having that idea, we then have the theorem that kind of summarize all these findings, and that's what we're doing in class. Okay. And we're using that result to treat the exponential distribution. This time we don't have to have a big multiplication. We'll work with the density function only, write it into exponential form. By analyzing this, since k of x equal to x, then summation of x becoming the sufficient statistic for theta. Theta is a parameter for the exponential distribution. We had a short discussion for the relation between the maximum likelihood estimator and the sufficient statistics. And you can see that the maximum likelihood estimator should be a function of the sufficient statistics, but the sufficient statistic might not be a maximum likelihood estimator. And if we have more than one parameter, you can have a joint sufficient statistics with a very similar treatment. We were looking at the two parameter situation. Normal distribution have two parameter, the mean and the variance. For that, we can come up with the factoring of the likelihood function. In this case, we notice that the summation of x is 1 and summation of x squared is another. Together, they are a joint sufficient statistics for theta 1, theta 2. And you can see the function x bar and s squared are jointly sufficient statistics for theta 1, theta 2 as well. Okay. And in fact, there can be a transformation from one to the other. And why is sufficiency so important? That's because they give us if you have sufficient statistics, you don't need additional information in order to just determine the parameter. And therefore, they give you a situation to shorten the discussion and limit the process only onto the function of the sufficient statistics. So maybe you can filter out many of the information that's redundant. All right. So the second theorem in the section is relation between unbiased estimator and sufficient statistics. So if you have a sufficient statistic for the parameter and then you have an unbiased estimator for the parameter, then the conditional expectation of the unbiased estimator based on the sufficient statistic will give you a revised estimator. This revised estimator is also a unbiased estimator since this is the expectation of the unbiased estimator, but this revised estimator will have a smaller variance. So that's kind of nice. All right, this is a mathematical proof of it. During class, we mentioned this, that we were able to prove that UY1 is unbiased because expectation of UY1 equal to theta. We'll also be able to prove that variance of Y2 is bigger than the variance of UY1. This is by writing the variance Y1 using the variance definition and enter the UY1 in the middle. Since UY1 is defined by expectation, we're able to simplify the right side of the equation and notice that variance Y1 is equal to variance of a UY1 plus a positive term. All right, so this process really provides an opportunity to start from unbiased estimator and arriving at another unbiased estimator that has a smaller variance, which is nice. Or you can also start the search for unbiased estimator with the smallest variance by consider only the unbiased estimator based on the sufficient statistics. So basically the estimator we intended to find should be a function of the sufficient statistics. So which give you a target format of your unbiased estimator. Another thing is the unbiased estimator that has the smallest variance should be unique. All right, so this is the part that we left. In class, the last part of the section is talking about independence. What we're talking about is really review one of the topics that we mentioned in section 5.5. Number 2, the second theorem in 5.5 was talking about, in 5.5, we talk about the distribution that are related to normal distribution. One of the things we're talking about is if x1, x2, and xn, they're from a normal distribution, then the x bar would also be a normal distribution, and the variance s squared, the sample variance s squared, is if it multiplied by n minus 1 divided by the variance sigma square will be a chi-square distribution. And another thing that we did not prove in 5.5 is that we assume that x bar and s square are independent from each other. That's what we assume in 5.5. And we take it as given, but we didn't prove it. Now we're able to prove it. The proof of it was that if you have two variable statistic y and statistic z, the y is a sufficient statistic for the parameter, and the z is a statistic that is free of theta, then y and z must be independent. So this is something we want to prove here. And then if we're able to prove this, then as a consequence, then see the variable x bar would be a sufficient statistic, and the variable n minus 1 times x squared, which we call z, would be a variable that's a statistic that's free of theta. If z is free of theta, y is a sufficient, z and y must be independent from each other. And why are they independent? We're going to prove it. right? But if that is true, if sufficient statistic and the statistic that is a distribution free of theta, so y is sufficient for theta, z is afraid of theta, then y and z must be independent. This is a very key result, and that's the foundation of the proof in 5.5 that the z and y, x bar and n minus 1 times a squared, they're actually independent from each other. Now, and in the 5.5, we have that n minus 1 times x squared is summation of xi minus x bar squared. This has a distribution that's free of theta. So how do we know that? So here, and how do we know that z is free of theta? We can prove it by looking at its marginal, its moment generating function for z. So the moment generating function for z is defined by expectation of e to the tz. Now z is defined by the summation of all these variables. Each xi follow a normal distribution. So if you want to find the moment generating function, which is defined by expectation, this expectation has to be calculated by integration. Since we have n random variable in z is a summation, z is defined by this summation of squares. So then this calculation has to be calculated by n layer of integration. So expectation is calculated by integration of the density function. So we're integrating this joint density function with, it's not triple integral, it's not double integral, it's n tuple integral. So this is an integration calculated expectation. We are trying to prove that this expectation, this moment generating function, is free of theta. So how do we prove it's free of theta? We're proving it by making a change of variable. We will take the xi minus theta as w. Okay, so then the xi minus theta in the exp function, they're all w squared. And then the dxi is the same as dwi. So dwi is replacing all the dxi. Wi is replacing xi minus theta. On the other hand, the subtraction, the xi minus x bar is replaced by wi minus w bar. So this is our integration now. And you see this integration is really a translation from xi, parallel translation to wi. Now you see this integration at the bottom. This integration, it's the n layer of integration. That's expectation of e to the tz. And this in this calculation, there's no theta, right? Because of subtraction. Because of the null theta, that means in this calculation of the moment generating function is free of theta. Therefore, the distribution of z is free of theta. And this is proving one thing. And then since this is z, which equal to the summation of square is free of theta, that based on the first sentence that we about to prove, that y and z, y equal to x bar, y and z will be independent from each other. All right, so now we want to prove y and z are independent, right? If y and z are independent, then this bottom y and z will be independent. This page about independence, the first sentence is any y that's sufficient statistic for theta, any z that's distribution is free of theta, then y and z are independent. The first one needs to be proved. The bottom half of it is talking about the 5.5. If you get normal distribution, you get y equal to x bar, z equal to the summation of square, then y and z would be independent based on the first half. So basically, the first half is a general result that needs to be proved. So here we are proving it. So let's prove it. How do we prove y and z are dependent? Suppose y is sufficient statistic for theta, z is free of theta. This proof is actually quite long, but we can outline the proof here. Number one is that you can see the conditional density HZY. That's conditional probability, conditional density of Z given Y. That's what you will need to calculate the expectation of GY dy theta. And the G1Y is the conditional density of y with respect to theta, since we know that y is sufficient of statistic for theta. So y is related to theta. And on the other side, z is free of theta. So in the density for z, there's no theta. So we have g2 theta. So g1 and g2 are density function for y and density function for z, since we're trying to prove y and z are independent. So in here, the first line is saying that this integration or this expectation is equal to 0. So the conditional expectation of z, conditional density of the hzy is free of theta, because we know that y is sufficient. Y is sufficient. Z is free of theta. And so hzy minus g2z is free of theta. This proof does have a normal distribution considerations here. Right, so basically the first equation is the reason that the hzy, the conditional density of z given y is equal to g2z, which means the z and y are independent. All right, this proof is kind of lengthy. That's why we don't have the actual proof. It's just the outline of the proof. We might have to work out many of the detail if we were to write it further out, extend it. So basically, the basic idea is if you want to prove the variable y and they are independent, you need to prove that the conditional density of z given y is equal to the density of z itself. So the condition and non-condition, these two density has to equal to each other in order to prove that we have independent variables z and y. All right, this was just try to write the theorem 5.5 there, so we kind of know the reason that we have to mention this, and this is another reason that sufficient statistics might be helpful, because when you have two separate functions, one is sufficient for theta, one is free of theta, then we are able to determine that these two must be independent from each other. Okay, so this is the sixth example, the last example for this section. We have a situation that we are going to apply what we just talked about. If you have one that's sufficient for the theta, one is free of theta, they must be independent. So here we have, what we have is a random sample from a gamma distribution. The parameter are alpha and theta. Then then the y equal to summation of xi is sufficient for theta because the gamma density is of the exponential form. So you can study the density function for gamma distribution and notice that the summation of xi is sufficient for theta. Here we're assuming that the only one that we are trying to estimate is theta, so parameter is theta. We're assuming the alpha is given, meaning that we don't have to determine the value for alpha. We're trying to determine the value for theta. So the parameter of concern is theta, not the alpha. And then we define a new variable, z. Z is called summation of ai xi divided by summation of xi. And we have to require that all these ai are not equal. If ai are equal, then ai can be factored out. Then the summation xi will cancel the summation xi in the denominator, and there's no point that it will not be random anymore. So all the ai cannot be all equal to the same number. So therefore ai does not have a common factor to factor out. And here we say that the variable statistic z has a distribution that is free of the spread parameter theta, because the moment generating function for z is the following. Right, so I'm trying to write on top of this just to explain why the z is free of theta. Basically, you can calculate the expectation e to the tz. You can calculate the moment generating function. We're displaying the integration for the calculation of the moment generating function. You have to take the e to the tz, which is e to the t times the summation over the summation, multiplied by the density function. This is really the density function of the gamma function, gamma density, and it's n gamma density. That's why we have n layer of integration. So we're repeating what we have earlier in here, and obviously we have to use a change of variable to show that um, this is also free of theta. Therefore, y and z. Y would be the summation of xi. Z will be this integration defined, division defined at z. Y and z are independent from each other. Okay, so how do we prove this n tuple n layer integration is free of theta? We'll do a change of variable. The change of variable is defined wi equal to xi over theta. Then the summation xi divided by theta is now summation of wi, and the xi, x2, x1, x2, xn multiplication divided by theta to the power n is now the w1, w2, wn to the alpha minus 1 power. So the dwi is now becoming dwi is dxi divided by theta. All right, so from the change of variable, we'll see that there's no longer a theta. Theta will be all combined because we did a division for the transformation for the change of variable. All right, so this is a quick proof that ETZ, the moment generating function for Z, has no theta, so Z is really free of theta, and that proves the independency. All right. One of the homework do require us to know this. So if you have any issue with the homework question, feel free to mention that. All right. And this is what I want to talk about just to finish the section 6.7 for sufficient statistic.